We're going to do something new, but at the same time, we've done it all before. We've literally done it all before. The only difference with what we're doing today is that we will have decimals. Decimals, that period, that point that is in some numbers, like 2.5. The topic is Introduction to Decimals. The objectives in this topic: know the meaning of place value for a decimal number and write decimals in words. Write decimals in standard form. Write decimals as fractions. Compare decimals. Round decimals to given place values. So half of this should look familiar. From the middle, we have ones, tens, hundreds going left, thousands, 10,000s, 100,000s, millions, then it would be 10 millions and 100 millions, and all of those ended with S. To the right side of the ones space, the right side of this as I'm referring to it, we have 10, excuse me, we have tenths, TENTHS, and then we have hundredths, THS, thousandths, THS, 10,000ths, 100,000ths, millionths. So the only thing missing is a oneths. And we have an exact mirror image of the left side, but instead of the S, we have THS. Tens meant 10 ones. Tenths means 1/10 of a one. Hundreds means 100 ones. Hundredths means 1/100th of a one. So now that we have our new place values, we're able to write or read decimals in words. Step 1, write the whole number part in words. Step 2, write or say "and" for the decimal point. Step 3, write the decimal part in words as though it were a whole number, followed by the place value of the last digit. We learned ones, tens, hundreds, thousands. Remember? The place value. Well, it turns out that there's more place values to the right of ones, and they mirror what's going on the other side. We have tenths, THS, instead of S. We have hundreds, THS, instead of S. What goes to the left of hundreds? Thousands. And sure enough, over here, we have thousandths with the THS. Ones, tens, hundreds, thousands, 10,000s, 100,000s. How about 10,000ths? With a THS. and 100,000ths with the THS. So ones becomes like a mirror, and to the left we have our place values we know already: tens, hundreds, thousands, 10,000s, 100,000s. To the right we have the mirror image of that, but instead of S we have THS: tenths, hundreds, thousands, 10,000ths, 100,000ths, millionths, 10 millionths, 100 millionths, billionths, 10 billionths, 100 billionths, so on and so forth. And separating the ones from the tenths is not a oneths spot, it is a decimal point. So how do we say a number? Well, how about 14.23? You're thinking, well, you just said it, 14.23. And yeah, we'll say that. But that's for simplicity. That's not what this number is. Just like you and I still slip and say things like 394 instead of 394. Or that one's kind of bad, actually. And you'll see why in a second. More like the way we say 204 instead of 204. We don't even say 204. We say O. O is a letter. 0 is the number. We should be saying 204 instead of 204, not 204. Anyway, I said that the 194 is actually pretty bad. That's because the decimal point is literally spoken as the word and. So if you ever say and in a number and don't mean the decimal point, you're saying the number wrong. How do we say the full number? Well, to the left, since we just learned about this right side today, obviously we know how to say the number 14 or whatever is to the left of the decimal point. We say it. So step one, we say 14 because we see that to the left of the decimal point. And then we say and because of the decimal point. That's how we say it, and. And then they come and cart us away because we're doing cheers for 14.23. Okay, problem ran away. Don't worry, I brought it back. I also fixed the framing a little bit. In case you didn't see, I wrote decimal point up here earlier. So, and that's how we say the decimal point. Now everything's fixed back in the frame. After we say the number to the left of the point and we say and for the point, then we say the number to the right of the decimal point, 23. 23. And then the last step in saying a decimal number properly is looking and seeing where the place value ends. So we said 23. Where does the 23 end? It ends in hundreds, tenths, hundredths. And so we say hundredths. 14 and 23 hundredths. 14 and 23 hundredths. Let's do another one. Three, 7.2.002. Well, how do we say this? 372. Decimal point. And how do we say 002? 2. And where does it end? Thousandths. $372 and 2 thousandths is how we say this number properly. And now I'm putting quotes around each of these so you can see the 1, 2, 3, 4 steps. 1, 2, 3, 4 steps. But obviously, the number itself, 372 and 2 thousandths, would all just be written as one thing. And we'll do that in the next example. We'll just write it as one thing. $504.9. 504.9. This would be 504, not 504, because where does the and go? Point and 9 tenths. $504.9. And we should be able to go the other way as well. And you're saying, wait, what? The other way? Go the other way. $5 and 7 tenths. Well, the and is the decimal point. 5 must be the number we write before the decimal point. And then we can't just start writing 7. What we have to do is look at where it ends. We see it ends with tenths. We have to identify the tenths place and make sure the number ends in that spot. So 5.7, there was no worry there. But that's not always going to be the case. Let's take a look at 3 and 2 hundredths. Well, the and is the decimal point. 3 must be what we write to the left of the decimal point. 2 hundredths. We can't just write 2 because that would be 2 tenths. So we have to see hundredths. We have to identify hundredths. It's the second one. And we have to make sure the number 2 ends there. So what do we fill in to keep the space? A 0. 3.023 and 2/100ths. To the left, if we had, let's say, a 0 there, and not even let's say a 0, this whole thing only works, what I'm about to say, if there's a 0 there. This 0 is optional. Here's why. If we wrote 0 and 2/100ths for 0.02, well, that would be the same as just 2/100ths, because 0 and 2/100ths is like 0 plus 2/100ths, and anything plus 0 is itself. So we wouldn't say 0 and 2/100ths. We would just say 2/100ths. And since we don't have a number, you don't necessarily need a number before the decimal point. Now, we wouldn't just say and 2/100ths either. In this case, the decimal point is silent. 0.02 is 2/100ths. We know there's a decimal point there because we're saying a number that ends in THS, and those are exclusively for to the right of decimal points. So even though we don't see 0 and we don't see and to say put a decimal point there, 2/100ths, since it ends in THS, would have an implied decimal point because we need to be here in the hundredths THS place value. Okay, so now we know how to say and write decimals. A decimal written in words can be written in standard form by reversing the procedure. For example, write this 106 5/100ths in standard form. Well, why was I driving home first? Where does it end? Because that's what we need first here. This ends in the hundredths spot. The whole number part, 106, that'll come first. And then the and, that's the decimal point. But the hundredths tells us where to put our 5. It needs to end in the hundredth spot and be the number 5. So 0, 5. We have this nice correlation between decimals and fractions, because if you've noticed, tenths certainly sounds like a fraction over 10. And 5/10ths certainly sounds like the fraction 5 over 10. And sure enough, it is. So we can speak the decimal, and that tells us what the fraction is. It's that simple. But we have to know how to speak the decimals. 0.36 is 36/100ths. That would be 36 over 100. Tenths, hundredths, thousandths, 2/1000ths would be the fraction 2/1000ths. Tenths, hundredths, 7/100ths. That's the fraction 7 over 100. If we had the decimal 0.3, this is Straighten that out a little bit. This is spoken as what? Well, we know our place value. Where does it end? It ends in the tenths spot, tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths. Ends in the tenths spot. It's spoken 3. This is 3/10, which sounds an awful lot like the fraction 3/10. And that's because it is. So what we're going to do is we are going to convert a bunch of decimals to fractions or mixed numbers. And then we're going to make sure our answer is completely simplified. Next. 0.11, tenths, hundredths, 11 hundredths. 0.5, tenths, 5/10, which reduces to 1/2. 0.15, tenths, hundredths, 15 hundredths. This reduces. They can both be divided by 5. 5 times 3, 5 times 20. 3/20. $1.51, tenths, hundredths. 1 and 51 hundredths. 1 and 51 hundredths. But watch this. This is also 151 hundredths. And when we convert this improper fraction to a mixed number, 151 divided by 100, same answer. Yet more confirmation about improper fractions being the same as their mixed number. The 0.016, tenths, hundredths, thousandths, 16 thousandths. This reduces because they're both even. Divide them both by 2. These are both even. Divide them both by 2. These are both even. Divide them both by 2. 2 over 125. This is how we convert decimals to fractions. More. 2.004, tenths, hundredths, thousandths. 2 and 4 thousandths. 2 and 4 thousandths. This reduces. They're both even. Divide them both by 2. This reduces. They're both even. Divide them both by 2. 2 and 1 2/50. More. 14.402 tenths, hundredths, thousandths. 14 and 402 thousandths. This reduces. They're both even. Divide them both by 2. $14 and I'm checking this one just to be sure. 14 and 201 500ths. I didn't think it reduced, but I wanted to make sure it'd be accepted. I haven't been checking this. I've been really confident until now. 0.4002 tenths, hundredths, thousandths, 10 thousandths. 4,002 10 thousandths. They're both even. Divide them both by 2. 2001 5 thousandths. $349.85 tenths, hundredths. 349 and 85 hundredths. We literally just say the number like we practiced way back when. And 85 hundredths. And we write it as a fraction or a mixed number. Whatever is coming out of our mouth when we say the decimal properly, that is how we write the fraction or the mixed number. Then we check and see, can we reduce this? Yes, they both divide by 5. But what is 85 divided by 5? I don't know, let's do it. 5 goes into 8 once, subtract, bring down 5. 5 goes into 35 7 times, evenly. So this is 17, and then 100 divided by 5 is 20. 349 and 17 20ths. We're going to go the other way now. Now we're going to start with fractions, and we're going to write them as decimals. Well, obviously, this is 0.5. And by that, I mean 5 tenths is 1/2. And 1/2 is 0.5. But surely there's some math behind that, right? Well, let's start by looking at fractions that have those numbers we kept putting when we went the other way. 10, 100, 1,000, 10,000, so on and so forth. 5 tenths, because it ends in tenths, we're able to just go, okay, tenths. And then what's our number? We'll write it in ending there. 5. There we go, 5 tenths. We're only going to be able to do that with numbers that have a denominator of 10, 100, 1,000, so on and so forth. So let's take advantage of this while we can. 26 over 100. 26 hundredths. Hey, hundredths. Decimal point, tenths, hundredths. Fill in the number we have so that it ends in hundredths. 0.26 or 0.26, they're the same thing. This time I'm going to leave a little bit of room after my equal sign because we're going to need it. 83 tenths. We can still use our trick because we have tenths. But this is an improper fraction, so we would be expecting a mixed number. We would be expecting something greater than 1. There's going to be something to the left of the decimal point. So we're looking for tenths. Identify tenths. Tenths. Write the number so it ends in the 10th spot. The 3 has to end there, which means the 8 gets pushed to the left of the decimal. 8.3. That's the easiest way to do it. But if you went to a mixed number first for some reason, that's okay. 83 divided by 10. 8 times 10 is 80, remainder 3 tenths, 8 and 3 tenths, 8 and 3 tenths. So you'll still get there. But it's easier to just think of it as 83 tenths, the number 83, ending in the tenths place value. $853 thousandths. Hey, there's another one of those place values. Tenths, hundredths, thousandths. We write the number 853 so that it ends in the thousandths spot. 0.853. Be careful. Remember, we want to write it so that it ends in the spot we want. 3 hundredths, tenths, hundredths. We want it to end here, but we still have the tenths place value. What do we put there? 0. So 0.03 or 0.03. You don't need the 0 to the left of the decimal point, but you absolutely need this 0 here to hold the place value. 0.3 would be wrong. That would be 3 tenths. 0.30 would be wrong. That's 30 hundredths, which is again 3 tenths. 0.03 is what we need. Nine, 2, 5, 6 over 1,000. 9,256 thousandths. It's improper though, so we're going to expect something to the left of the decimal point. But let's identify thousandths. Tenths, hundredths, thousandths. We write the number 9,256 ending in that spot, which means the 9 gets pushed out to the left. 9.256. $29 over 1,000. Decimal point, tenths, hundredths, thousandths. The number 29 ending in thousandths, a 0 for placeholder. 0.029. $578 tenths. It's improper, so we're expecting something to the left of the decimal point. Tenths, The number has to end there, which means the 57 gets pushed over the decimal point. 57.8. 57 and 8/10. 7/10. Tenths. The number 7 ending there. Remember, I said we like that. That's a shortcut. I'm avoiding giving you the long way as long as possible. 14/25. Well, there is no 25ths decimal spot. Decimal literally means power of 10. Is it time for the long way? No. What? Why not? 25 might not be a nice number, but it's nice enough that there's an equivalent fraction with a nice number. When we have 14/25, we can recognize that if we multiply by 4/4, if we multiply 1 and not change the value, 25 times 4 is 100. So 14 times 4 is 56. We get 56/100. Don't reduce. We want to turn this into a decimal. We reduce, we're just going to get 14/25 back. That doesn't help us. We're going away from that. 56 hundredths, decimal point, tenths, hundredths. The number 56 ending in the hundredth spot. Let's see how long we can use this workaround to turn it into the nice power of 10 trick before we have to learn the long way. 3/4. Do we have to learn the long way? Well, the question is going to be, can we multiply 4 by something and get one of our nice numbers? We sure can. We can multiply 4 by 25. To keep it equivalent, we would multiply the top by 25 because 25/25 is 1. And we get 75/100, 75 hundredths, tenths, hundredths, the number 75 ending in the hundredth spot. 0.75 is 3/4. Hey, maybe you knew that one. You got to know the math. 3/25. We can use our trick. 25 times 4 is 100. So we do 3 times 4 is 12. 12 hundredths, tenths, hundredths, the number 12 ending in the hundredth spot. If I'm going too fast, feel free to pause, catch up, pause and try, see if you're right. 13/5. Can we use our trick? Yeah, we don't even have to go all the way up to 100. 5 times 2 gives us our nice number of 10. 13 times 2 would be 26. Improper, so we're expecting something to the left of the decimal point. Tenths. The number 26 ending in the 10th spot. 2.6. If we had 0.63 and 0.68. So if we had 63 hundredths and 68 hundredths, we would like to know whether these are able to be compared with this symbol, with this symbol, or with this symbol. This one is less than. This one is greater than. This one is equal. The way you can keep less than and greater than straight is that the L in less, when you tilt it, makes the less than shape. Less. See it? I like to remember it by using our old friend Pac-Man. Yes, Pac-Man from the Pac-Man game starring Pac-Man. Pac-Man is hungry all the time. He likes to eat. If given the choice between the number 1 and the number 2, Pac-Man would choose to eat the number 2 because it is more than number 1. And when you like to eat, you like to eat a lot. So you can remember Pac-Man always chooses to eat the larger number. So 1 is less than 2. This way, the greater than symbol, 2 is greater than 1. How do we know? Because Pac-Man would choose to eat the 2 every time. 2 is greater than 1. And we know what equal means, that they're the same. So when we're comparing decimals, we want to take it digit by digit. Obviously, if we just look at the numbers before the decimal point, if they are different numbers, it is a very easy problem to do. However, when they are the same number, we have to go place value by place value. So 0 point, they're the same so far, moving over. 6, they're the same, moving over. 3 and 8, these are different. They're the first one that's different, so they're what we will compare. Since 3 is less than 8, 0.63 is less than 0.68. Let's compare more numbers. 0.35 and 0.32. Zeros are the same. Threes are the same. 5 and 2 are different. Compare the 5 and the 2. 5 is greater than 2. So 0.35 is greater than 0.32. You're thinking, okay, this is pretty simple. Don't fall for any tricks. 0.297 and 0.3. Maybe a rushed reaction would have you go, wait a minute, this has so many more digits than this one. This one must be greater than, but that would be wrong. Because remember, we have to go digit by digit. It doesn't matter how many we have. What matters is the zeros are the same. The first number that's different is this 2 and this 3. That is what we compare. 2 is less than 3. So 0.297 is less than 0.3. And that makes sense
Because 0.3, it doesn't matter how many zeros we have afterwards. That's something that's fun about decimals. We can keep adding zeros. We can keep adding zeros and not change the value. So when it's 3 digits compared to 3 digits, we see 297, we see 300. 297 would be less than 300. So we can't just compare looking at 297 versus 3, because 297 would be bigger than 3. We have to go digit by digit, because that will give us that situation, the same answer as the situation where we can clearly see 297 and 300. If you want, when you see a comparison like this, if this is 3 digits and that's 1 digit, go ahead and put zeros in. Help yourself out. But still show that you're comparing these. Okay. Now that I've said all that, 0.514 compared with 0.51400. Don't be fooled. We've got 3 digits here. We've got 5 digits here, but the last 2 are 0. Let's match that with a couple zeros over here. And what do we clearly see? We clearly see that these are equal. It didn't matter that this only had 3 digits past the decimal point, and this had 5 digits past the decimal point. What mattered was the zeros were the same, the 5s were the same, the 1s were the same, the 4s were the same. These zeros at the end don't matter. And if we match them up here, the zeros are the same, the zeros are the same. So equals.
We're going to compare 26.208 and 26.28. One of these has 3 digits past the decimal point, 3 decimal places. The other only has 2. So to make sure we're going to be able to compare the whole way, add a 0 to the one that had 2. So 0.28 becomes 0.280. 26 and 26, those are the same. Then the decimal points. Then the 10th spot, 2 and 2, that's the same. The 100th spot, 0 and 8, those are different. The one with the greater number, the 8, is the greater number overall. So 0 is less than 8. So 26.208 is less than 26.28. .12 and .026 are being compared here. We only have 2 place values, decimal place values on the left. We have 3 decimal place values on the right. So add a 0 on the left so that they both have 3. Now we're going to be able to compare the whole way, but we don't have to go very far. The zeros are the same, then the decimal points. Then we have a 1 and we have a 0. The 1 is greater than 0, so the 0.12 is greater than the 0.026. Rounding. We round the decimal part of a decimal number in nearly the same way as we round whole numbers. The only difference is that we drop digits to the right of the rounding place instead of replacing them by zeros. For example, 63.782 rounded to the nearest hundredth. We look at the hundredth spot. We see an 8. We look 1 to the right. We have a 2. Is a 2 5 or greater? No, it does not round up. We normally would have replaced that 2 with a 0. Instead, we just drop it. The 2 doesn't round the 8 up, and it's no longer important. When we round a number to the nearest hundredth, our answer will be in hundredths. If we were rounding to the nearest thousandth, our answer will be in thousandths. If we're rounding to the nearest tenth, our answer will be in tenths. If we round to the nearest whole number, then we don't have a decimal at all. So to recap that, locate the digit to the right of the given place value. If it's 5 or greater, add 1 to the digit in the given place value and drop all digits to the right. If the digit is less than 5, just drop all the digits to the right of the given place. 326.4386, 326 and 4,386 10,000ths. It's given in 10,000ths, but we want it to the nearest tenth. That means our answer will just be into the tenths place value. So identify the tenths place. That's a 4. Locate the digit to the right of the tenths place. That's a 3. It is not 5 or greater, so we just drop it and everything to the right. 326.4. 326 and 4/10 is that number rounded to the nearest 10. Let's round 0.5942 to the nearest thousandth. It's going to end in the thousandth spot as opposed to the 10,000th spot that it's ending in right now. Locate the digit to the right of the given place value. The given place value is thousandths. That's a 4. 2 is to the right of that. Since it's less than 5, we drop it and all digits to the right. There's nothing to the right of it, so we're just going to drop it. 0.594, 594 thousandths. What about money? Round $0.067 to the nearest cent. Well, we know dollars and cents. We live with dollars and cents. Cents has 2 decimal places. This is asking us to round to the nearest hundredth. Locate the digit to the right of the given place value. The given place value, cents, that's a 6. The digit to the right would be a 7. That is 5 or greater, so we round up. The 6 becomes a 7. And then the 7 is dropped. So $0.067 rounds to 7 cents, or $0.07. An aquarium costs $245.69. Round the price to the nearest dollar. The nearest dollar would be the nearest whole number. We're going to write this without any decimals at all. Find the given place value. That's the ones place. That's a 5. To the right, we have a 6. That is a 5 or greater. That rounds the 5 up to a 6, $246. And I have a problem with the answer as written. This is a mistake. I'm going to correct it. There we go. I got rid of the 0 cents because rounding to the nearest dollar would be $246. 246.00 implies that we're rounding to the nearest cent, and that is not the case here. Water bills in Mexia are always rounded to the nearest dollar. Round a water bill of $24.62 to the nearest dollar. Rounding to the nearest whole dollar means rounding to the ones place. So I already fixed this one. 24.62. The ones place is a 4. To the right of the ones place is a 6. That's going to round that 4 up to a 5. So $25. And that's not a decimal point at the end. That is the period at the end of the sentence. And that is it for this topic. The topic is adding and subtracting decimals. The objectives in this topic are add or subtract decimals, estimate when adding or subtracting decimals, evaluate expressions with decimal replacement values, simplify expressions containing decimals, and solve applications that involve adding or subtracting decimals. So it's a pretty simple, straightforward process to add or subtract decimals. Step 1, we write the decimals so that the decimal points line up vertically. And then we add or subtract as with whole numbers. Finally, we place the decimal point in the sum or difference so that it lines up vertically with the decimal points in the problem. So line up the decimal points, add or subtract, make sure the decimal point is in the same spot in your answer. Recall that zeros may be inserted to the right of the decimal point after the last digit without changing the value of the decimal. This may be used to help line up place values when adding or subtracting decimals. For instance, 85 minus 13.26 becomes 85.00 minus 13.26. Instead of having 2 empty spaces after lining up the decimal points, we can stick 2 zeros after the decimal point after 85. Then we would just subtract like normal, and the decimal point lines up with the decimal points in the problem. So let's add 0.004 plus 0.085, 4 thousandths plus 85 thousandths. We line up the decimal points. Then we add like normal. Once the decimal points are lined up, we would add 4 plus 5 is 9, 0 plus 8 is 8, 0 plus 0 is 0, 0 plus 0 is 0. Finally, stick the decimal point right underneath the decimal points lined up in the problem. So 0.089. So if we have 6.7 plus 3.2, to add these, we line up the decimal points and add like normal. Where the decimal points are in the problem is where the decimal point goes in the answer. 7 plus 2 is 9. 6 plus 3 is 9. 9.9 would be the answer. That's all there is to it. It's just like adding.
We just line up the decimal points. 7.4 plus 5.16. Line up the decimal points. 7.4, 5.16, and then add. If you have empty spots due to lining up the decimal point, what can we fill it in with? What do you think? 0. So line up the decimal points, decimal point into the answer. Add like normal. 0 plus 6 is 6. 4 plus 1 is 5. 7 plus 5 is 12. 12.56. So how about 107.563 plus 42.07? Line up the decimal points. 107.563, 42.07. So much interesting happening here. We have an extra place value. We can fill in a 0 there. And when we do our adding like normal, we'll have carrying. 3 plus 0 is 3. 6 plus 7 is 13. Carry the 1. 1 plus 5 is 6. 7 plus 2 is 9. 0 plus 4 is 4. 1 plus nothing is 1. 149.633. I can't really make that more interesting, it turns out. I guess what I should mention, just to be clear about it, is if we had something like 470 plus 53.11, we don't see a decimal point in the first number. But we know that the decimal point exists at the end of the number. So 470 is the same as 470.0 or 0.00, as we're going to need here to line it up with 53.11. But after that, it's just our normal addition. Just like with regular addition, if we're asked to find the sum of something, that means add the numbers. Subtraction is going to work the exact same way. Line up the decimal points, subtract like normal. 11 minus 7.5. Well, just like with that addition one, when we don't see a decimal point, we know it exists at the end of the number. So 11 is 11.0. Minus, line up the decimal points, 7.5. Decimal point goes where it goes in the answer. Line it up. And then subtract like normal. 0 minus 5, we can't do it. What do? We borrow. That 1 becomes a 0. This 0 becomes a 10. 10 minus 5 is 5. 0 minus 7, we can't do it. We borrow. That 1 becomes a 0. This 0 becomes a 10. 10 minus 7 is 3. 3.5 would be the answer. We can check with addition if we want. Add up 3.5 plus 7.5, and what do we get? 11.0, which is 11. So 3.5 is the answer when we subtract. Let's do another one with subtraction, bigger numbers, missing digits. 565.3 minus 56.02. So I'm giving this one to you lined up already. We have a missing digit here. In order to do our subtraction, we need to see that that is a what? A 0. And except for putting that decimal point in the line, it's a straightforward subtraction problem. 0 minus 2, can't do it. Borrow, 3 becomes a 2, 0 becomes a 10. 10 minus 2 is 8. 2 minus 0 is 2. 5 minus 6, can't do it. Borrow, 5 becomes a 15. 15 minus 6 is 9. 5 minus 5 is 0. 5 minus nothing is 5. 509 and 28 hundredths. 509.28. How can we check it? We can check by adding. 509.28 plus, line up the decimal, 56.02. 565.3. That's what we started with. So we know we're right.